All right, so yeah, it looks like overall you guys did really good, especially these first questions. Great of students got it right. So look how many students are getting these right. It's awesome, awesome, awesome. All right, okay, looks like number 7 was pretty tough. All right, then the last few questions looks like pretty tough. Yeah, right. So I think the best way for me to go through this is actually start with the last one and work backwards. Right. Oh, guys, I should tell you how I'm scoring those two in the grade book is as long as you guys are trying, then you get full credit. Right. But if you miss a bunch of questions, say like out of 18 questions, if you only got like 7 or 8 questions right, then I might look into it and see where it tells me how much time students spend on each question. Uh, if I see you spent like 2 seconds, 3 seconds, 2 seconds, 4 seconds, then I know you Christmas treat it. So it's like, okay, well, in that case, you didn't actually apply any effort, so I didn't give you full credit for that. But as long as you tried, then you get full credit. And so let's start with this last one. So it's only a few guys got this one. I've got it. Okay. Got an acrobat initially hanging from a bar over platform with negligible mass attached to a spring as shown. The acrobat then releases and falls to the platform. When the acrobat lands on the platform acrobat continue moving downward until they momentarily come to rest when the spring is compressed to maximum distance. Huh.
How'd you get the wrong?
Consider. All right. So this question is all about systems. Consider a system consisting of only the acrobat and the spring. Guys, notice if you pay really close attention, what did they leave out of the system? Yeah, the Earth, right? And I've been telling you guys, whenever they leave the Earth out of the system, are you allowed to consider MGH, the gravitational potential energy? No, not really, right? Now you are allowed to consider kinetic energy, 1/2 mv squared for this guy being in motion. You're also allowed to consider 1/2 kx squared, the energy that can be stored in the spring. But you're not actually allowed to consider the MGH, okay? Right? Which means that, guys, would this be considered a closed or an open system? This has to be a what system? Open. Yeah, guys, it's got to be open because there's an external force now. The external force would be from the Earth, which is not part of the system. Okay, this is an open system, so energy is not actually conserved. Okay, because it's an open system and there is an external force. Okay, which of the following correctly indicates the moment when the Acrobat spring system has the largest total mechanical energy and provides justification.
Yeah.
Again, if they also threw in the Earth, guys, if they throw in the Earth to make it a closed system, what would the answer have to be? Guys, look up here. Almost everybody missed this. Guys, look up here. Right. Guys, if they also threw in the Earth to make it a closed system, what would the answer to that question be? The energy would be the same everywhere because it would be a closed system. Energy is conserved. Right? The fact that it's an open system means they're even allowed to ask this question for it to be something. Right? So here's what I'm thinking. Guys, at the top, when he's holding on to the bar, or maybe just after he's released, his speed is equal to what? 0. So his kinetic energy is equal to what? 0. And that spring is not compressed because we're saying the platform has no mass, has no weight, right? So there's also no energy in the spring. So what's the total energy in that system? Yeah, 0. 0 energy, right? Now, when he's landed on the platform and it starts to compress it, okay, no, he has been accumulating kinetic energy. Isn't that true? As he's been falling, so the energy system is increasing the entire time he's falling. Right? Then when he compresses that spring to some maximum compression, isn't all the energy in the spring at that point? Right? And there's some 1/2 kx squared. And actually, couldn't that be maximum energy? Right? Um, I think that would be the answer. No, he is also falling into so guys, is the Earth also pulling on him while he's compressing the spring? Yeah, and so even more energy is coming from that. Because if there was an option to say, like, right as he's landing on the platform, it has a ton of kinetic energy, I mean, that might be a possibility, but I think there would be even more energy when the spring's maximally compressed. So that would be the best answer. Okay, let me see if that's what they chose here. The acrobat is on the platform. Yeah, when it comes to rest, that's when it's maximally compressed because he's compressed at the maximum amount. Right? Do they? Okay. Um, yeah, a lot of you guys picked A immediately after release from the bar because the greatest distance above the lowest point, greatest amount of gravity. Okay. Yeah. That MGH you are not allowed to consider because this is only the Acrobat spring system, not including the air. Hey, you guys got that? Right. Actually, you know what? One more detail I got for you guys. I'm gonna dig through the posters from far in the future. Because remember one more that was for you guys. Yeah, I found it right here. Here. And flip back over. Okay. Okay. Okay, so we are considering Really just these two forms of energy. That's all it counted. Right. This one didn't count at all. Okay. Right. So here's a related question that wasn't going to show you guys for a few more months, but there's a whole uh, unit on just like spring oscillation. Right. So eventually this will come up. It's like, what if you have this? What if you have just a spring? It's hanging out here. There's nothing on it, and then you take a weight like this weight right here, and you take it, and you very slowly lower it until it comes to rest. So be right here, guys. If it's at rest, is that called equilibrium? Yeah, at rest would be equilibrium. So is the down force equal to the up force? Right. But what if you did so instead? What if you hook it on here and then you just let it go? And it overshoots the equilibrium. There's some maximum stretch and then oscillates. Right. Guys, would the maximum stretch be more than the equilibrium stretch? It sure would be. Right. Do you guys see that? That would be the case. Right. Now, if you let this oscillate like 100 times, it eventually comes to rest. Let's say it's a tiny bit of frictional loss. Then it might eventually end up here. Right. Okay. Now, what is this maximal stretch compared to this equilibrium stretch? Uh, and the important thing for this class is, do you know how to think about that? Do you know how to set that up? Well, for equilibrium, can you just say the forces sum to zero? That's what equilibrium is, right? The mg down matches the kx up. So you could solve for x, and it ends up being this expression. You guys see that? Okay. Now, guys, for the maximum stretch, it's not equilibrium. Guess what, guys? Guess what method you use to solve for the maximum stretch? Conservation of energy. Yeah, exactly. Guys, at the top, when I hang this weight right here, it has all what type of energy? Gravitational potential. Isn't that mgh? Right, mgh. Now, if I define that h as the distance above the lowest point, then that h is also x max. Is that true? Right. Now, what about the point where it finally does come to rest? Now, it's not permanently at rest. It's just momentarily because it's actually turning around, right? Right. Guys, where'd all the energy go? Yeah, into the spring. And the formula is called what? 1/2 kx squared. Right. So can you still solve for x max? It shows up in two places now. Can you solve for that? Right. And well, I've done it ahead of time. Right. Now, guys, now if you compare these two stretches, right, the equilibrium stretch versus the max stretch, they're almost the same, except they're off by a factor of what? 2. So if this came out to, for example, 5 centimeters, what would this have to be? 10 centimeters, because it's twice as much. You guys see that? Right? Right. So if they ever say, like, how much is a spring stretch, you have to be really careful about, well, what scenario are we talking about? If they say you slowly lower it, bring it to rest, that's an equilibrium scenario, and this is the answer. If they say you let it go and it goes just to maximum and then like oscillates or something, then it's a conservation of energy. And this is the answer. Okay. Right. So yeah, you'll definitely see that at some point. Okay. All right, and that's the scenario that we're looking at there. All right. All right, number 17. Ooh, figure 1, a person uses a pulley to lift a belt. Hey, you guys got to build some pulley systems tomorrow. Hey, guys, let's talk about mechanical advantage a little bit. Just look at these two figures. Guys, on the first one, what would the mechanical advantage be lifting the belt? Could you say there's no mechanical advantage at all? Right? And mathematically, that's called a one-to-one mechanical advantage. So for every, like if this bell weighs 50 newtons, she has to apply 50 newtons of force. And if she pulls 1 meter, how far does the bell move up? 1 meter. Is it? But guys, on figure 2, see if you guys can figure this out. What's the mechanical advantage in figure 2? 2 to 1. Guys, it is 2 to 1. You guys see that? Like if the bell weighs 50 newtons, guess how much she has to pull with on her side? 25 newtons, and it lifts the bell. Because the tension in this rope would be 25 newtons, and that applies 2 times to the bell. Is it 25 up here and 25 up here? And that lifts the 50 Newton bell, right? Now, what about this? What if she wants to move the bell up 1 meter? How much rope does she have to pull? 2 meters. 2 meters of pulling on her side lifts the bell up 1 meter. Okay, so it's a 2 to 1 mechanical advantage. All right, so I see that just from the figure. The person pulls down at, oh, they're bringing in speeds. Now, that's an interesting scenario. So that's like the rate change in distance. I just couch the question to you guys in terms of like, she wants to move up so many meters. They're talking about meters per second. Huh. Okay. Oh, power is delivered to the bell. Now, let me pause right there, because as soon as they mention the word power, I'm already thinking about this one right here, right? Okay, so power is work per time. And then that you can rearrange that and get that as force times velocity. You can do that, right? So I'm thinking this is probably going to be applicable. Let's see if that's true. In figure two, the person uses a double pulley. The person pulls on the rope. Also, at the same constant speed. Same constant speed. Now, I forget what the question is, but let's go back over here. Guys, if it's the same speed, well, um, see, if she's pulling with, well, I guess it's the same speed on which side. If the bell's, guys, if the bell's going at the same speed, bell's going at the same speed, right? And the bell weighs the same amount as before because the weight of the bell didn't change, right? Then would that be the same power, same speed, same weight, same, right? On the other hand, if they phrase the question like, if she pulls the rope on her end with the same speed, but she's only pulling with half the force, that would be half the power, wouldn't it? Right. Okay, so it depends exactly how they phrase the question. So what they say here, she pull. Oh, she pulls down on the rope at the same constant speed. Okay, so it was the second thing I said, guys. She's pulling the rope at the same speed. So is the bell moving up at the same speed? No, guys. The bell's moving. How's the bell moving now compared to before?
2 times slower.
Yeah, 2 times slower. It's only moving at half the speed. You guys get that? Right. Here, let's go back over to back over here. Remember, if the work is the same on both ends, output input, right, and the time is the same, time passed is the same, right? The power will be the same. Power input equals power output for this case, right? So, uh, from from her point of view, she's pulling with the same speed, but with half the force. So isn't that half the power overall? Right. Well, the same story should be true on the side of the bell. Now, the bell's weight didn't change, so the overall force didn't change, right? But I mean, it was 2 ropes, right? But it would be going half as fast, right? So then it would come out to the same power. So if it's like, like 100 watts on her side, it would be 100 watts on the side of the bell. Like that. The bell moves upward with at a constant speed, but they even gave it to you right here. The speed of the bell is half the speed that it was in figure one. They didn't even have to tell you that. They're giving you an extra hint, right? The power delivered to the bell in figure two is P2, right? Which the following correctly compares P2 to P1 and provides valid justification. Actually, didn't we just figure that out? Guys, what's the exact answer? Half. Yeah, it's half. P2 is half of P1. Right, you guys get that? Right, here, I'll go through it one more time. Right. So, powers work per time. Now, the work input output is the same on both sides, the pulling side and the bell side, right? And the time interval is the same. So everything else follows, and the power is the same on both sides. 100 watts in equals 100 watts out. Right? Now, she pulled with the same speed on her side, but in figure two, she only had to pull with half the force. So half times whatever the speed is half the power of the original, right? So figure two, she's pulling with half the power of figure one, right? Or you could think it from the bell side. Now the bell weighs the same as before, so the total force is the same. Right? But the bell moves with half the speed. So however you think about it, it's getting half the power. Right, so it should be half. Right. And they just went with an inequality because the force exerted on the bell is the same, but it's moving with less speed, right? Half the speed. That's it. Right? Now, when I should point out too, guys, when they say the force exerted on the bell is the same, that right there, right? They're talking about the combined force because isn't this rope pulling up on the bell twice? Because right, you guys see pulling up there and also pulling up there. Right, so if you combine all that force, it's the same as the weight of the bell. Yeah. Oh yeah. Okay, so you guys go there. All right. This one. Oh, we got a sled released from point A on a track where friction is negligible. Okay, so we have a zero friction situation. So there's no frictional loss. If you want to, maybe you could sort of think it's like a marble going on a track or something. Or, just ignoring the rolling part. Point A, vertical position. H naught is shown. The sled remains in contact with the track until the sled passes through points B and C. Here, guys, here's a little detail that they did have to mention. Because, guys, if they did not mention that detail, is it possible, guys, could you get the sled to fly off the track at point C, just fly off the track? Yeah. I'm thinking especially of two conditions. If it's going too fast, guys, if it's going too fast, would that be true? And that could be true if H naught is way too big, it could be going too fast at point C and fly off. Right. Also, guys, if you think back a couple of weeks ago, think about radius of curvature. Could you think of a circle? I'm tracing out a circle with my mouse cursor right here. Could you fit a circle flush to the curve at point C right here? Right? And if that radius is too what? That'd make it susceptible to flying off the track. Too small, exactly. Yeah. If this radius curvature is too small, it's more likely to fall off the track. Versus if it's really big, that flattens out the track and it's less likely to fly off. Right. Anyway, they said don't even worry about that. It just remains in contact with the track. Okay. All right. Let system A consist of the sled only. Okay, so we're back to a systems equation. Sled only, which means you can only consider the one half mv squared, the kinetic energy. And system B is the sled in the earth, which is that would be a closed system, wouldn't it? The sled in the earth is a closed system. Now you're allowed to consider also the MGH. Which of the following correctly indicates the point which the mechanical energy is a maximum? Okay. So let's start with the closed system because I'd probably ask it like that myself. So system B. Guys, system B, the closed system. Where's the energy the greatest?
The same everyone.
It's the same everywhere. Yeah, it's a trick question, but you guys got that? Yeah, it's the same everywhere because it's a closed system. Energy is conserved. Right. Now, for system A, it consists of only the sled. You're only allowed to consider 1/2 mv squared, but the MGH doesn't count. Right, just 1/2 mv squared. So how much energy is at point A? Nothing. Right, zero energy. If you're only focused on the sled. Okay. So how about at point B? Isn't there a bunch of 1/2 mv squared? In fact, it would have to maximize at point B, wouldn't it? Because when it starts to go uphill, then it's losing some of that kinetic energy. So I think system A maximizes at point B, and system B should be the same everywhere. Right? So that looks like I think option C, right? Is that option C?
Sure.
Okay. Is there any question why it would be option C? Okay. Let's see. Yeah, it sure is.
Oh, very good.
Huh? All right. All right, question 15. The exact same scenario, right, but different question. Which of the following correctly relates how the speed of cart depends on the vertical position y after it's released? Right. Now, the answer is not option A, obviously, because it doesn't have the gray box. But I do see the format of the answer they're looking at. So they're saying speed is proportional to something. Yeah. Right. No, for proportionality, I usually just use a little tilde sign. Some textbooks use this this alpha lookup proportion. Right, so you might see those interchangeably. Right, so speed is proportional to what? So let's set up an equation and solve that. Speed related to height, right? Let's see. Cart. Right. Right. So let's set this up. Anyways, we got something like this going on.
I don't know what
Call this like H. Well, let's call it H, right? And then in general, the distance up could be like some value y, something like that, right? So maybe I want to do sum of energy initial equals sum of energy final. I can say that, right? Okay. Now, guys, at the beginning point, what is its energy equal to? Here, and let me go to your options. Here's your options right here. Guys, at the very beginning, at the very top, which one? MGH. Right? MGH. So it's all MGH, and there's nothing else. There's nothing else. Now, what guys? What about some arbitrary point? Like, what about this point right here? And if that's a point, guys, if y is a variable, could this be y at some point? Could that be y? Okay. In that case, it has some mgy plus it's going to have some 1/2 mv squared left over. Isn't that true? Right? You guys get? And we're sort of solving for this v right here. What's the speed? You guys get that? Okay. So let's see. I think I could subtract over the mgy. So you could say mgh minus mgy results in 1/2 mv squared. Ooh, guys, could you factor out an mg on the side? So mg and then h minus y results in 1/2 mv squared, like that. Or No. If this was a free response question, I would definitely be writing out every single one of these steps. Starting with this top step, so I can tell the AP grader I know like how to think about this. Okay. But maybe if you do enough of these, you could eventually, just in your mind, sort of snap straight to this one. You say, okay, well, I see this height change. Guys, is this height change right here equal to h minus y? Yeah, this total h minus this little y down here. Okay, so you might be able to sort of visualize that from the beginning. Okay. Ooh, guys, could I at some point cancel out the m? Hey, if I'm just solving for v, then it doesn't matter how massive the sled is. I can cross multiply the 2. So I got 2g h minus y is equal to v squared. Okay. And last step is take the square root. So v is the square root of 2g h minus y. Right? Guess that? No, that should be the exact answer. And I did see from the format of the answers, they're doing something with the proportionality. So I'm going to make a guess. I'm going to make a guess that v is proportional to, well, who knows exactly how they wrote it, but there's probably a square root and probably an h minus y. Right? So I'm kind of looking for that, but I know this is the exact answer. So if they threw in a 2 root of g, then that would also be okay. All right, let's see if I see anything like that. Yeah, all right, that's it exactly. So as a proportionality. All right, so you guys get on that one? How to solve that?
Do you know that MCI?
All right, we got two blocks, horizontal surface connected by a spring. A rope pulls the blocks with a constant force, and both blocks move with the same acceleration to the right. Uh, and notice, of course, there's a spring connecting both those blocks. Is the spring potential energy zero? Why or why not? Okay. Guys, if the system is accelerating, that means that, well, I mean, if both blocks are accelerating, then that includes this block that's in the back. Okay. So, guys, does this block in the back have to have a net force on it? Yeah. Right. And so, is the spring pulling with the force? Yeah, I think that also has to be the case. Like, they didn't say anything about friction. I don't think they're being like super tricky with it. Yeah, I think there has to be a force in the spring. Guys, if there's a force in the spring, is the spring stretched at all? Yeah, F equals kx. That reminds me of Hooke's law, F equals kx. And if that's true, if there's a k and an x, then is there some energy stored in the spring? Yeah. So, to their direct question, is the spring potential energy zero? What do you guys say? Yes or no? Yeah, the answer has to be no. Has to be no. Because the spring has to be stretched some amount. So if I see an answer choice like that. Okay, yeah, most of you guys got this one. No, because the spring must be exerting a force. F equals kx. Therefore, there must be energy in the spring, 1/2 kx squared. Okay, so you guys go with the spring? All right. 13. A motor delivers constant power P. All right, so yeah, I forget what the question is, but immediately I already start thinking about this. Maybe I don't know. We're gonna see if this is applicable. To a toy car mass m on a straight level track, the car starts from rest, and at some time delta t, the car has speed v. The same motor delivers the same. Okay, it's the same motor with the same power to another car with twice the mass. What will be the car speed after the same time interval? Ah, okay. So we're comparing speeds, the same power for the same time. Okay. See, same power, same. Guys, if you do the same power for the same time, did you apply the same work to both cars? Same power for the same time is the same work. Is that true? Yeah, it is. It is, right? Right. So actually, I'm just going to work through that. I'm just going to go straight through work. Is that okay? Same power, same time, results the same work. Okay. Right. No, I think it would be probably different. Hold on. Well, here, it'd be a little tricky to work that one. I'm just going to go through this one. Okay. So I'm going to go, what's the, well, I'll spell the word work on car 2 versus what's the work on car 1. And that results in some 1/2 mv1 squared for car 1. Is that true? Or here, I'm going to change this to 2 as, sorry, that's car 2. I'm doing car 2 first, then car 1, because I'm going to set up a fraction. And then work on car 1, 1/2 mv squared. and this is V1. Okay. Okay. So the only difference in the cars is the mass. I got double the mass of car two, and that's going to result in some speed two. And the car one just had mass one. But these are the same work. So the works are equal to each other because it's the same power for the same time. So the works are the same. So I can set this expression equal to this expression. Is that what I want to do? Yeah, let's just do that. Okay. So 1/2 times 2m times v2 squared equals 1/2 times m times v1 squared. So, okay. Now, regardless of what the mass of the car was, is it canceling? Guess I'll get rid of this 1/2 also. Okay, get something like that. Now, what is v2 in terms of v1? Now, there's a few different ways to finish this out. But here, I was really trying to set up a fraction, so I'll just kind of go back to that. Okay, so can I divide over this v1 being squared? And then maybe divide over this 2? So that would be v2 squared divided by v1 squared, because I just divided this v1 squared over. Okay, equals. And I still have a 2 hanging out over here, so I'll just divide that over to the other side. That can be true, right? That's still a true statement. Okay. Right, now I can take the square root of both sides. So if I do that, square root, that's going to give me the ratio of the speeds is square root of 1/2, which is also 1 over the root 2, which is also root 2 over 2. Which is 0.707. Okay. So if I saw any answers that look kind of like that, that could work. See, alternatively, you could have just done the algebra a little bit different. You could divide over the 2 first, then take the square root. You still basically get the same thing. Right. The v2 is this ratio times v1. Okay. So it should be the answer. Okay. Is there any question about that? You guys good? All right. So what will be the car speed? V2 should be 1 over the root 2. Yeah, there it is. So the original speed divided by the root 2. Okay. Right. Ooh, this one. This one. We got a fan attached to top of a block is shown. Block is released from rest. And the fan exerts a constant force. And the opposite of block's motion. So block is trying to slide down, but the fan is blowing it, trying to slow it down, basically. Block slides the distance d1 along the incline, transitions to a horizontal surface. Eventually comes to rest at distance d2. So they didn't mark that, but maybe some distance d2 comes to a stop. And they don't need to worry about friction. We're just focused on gravity's pulling it down, and the fan blowing is trying to bring it to a stop. It eventually does. Which of the following correctly describes the relationship between those distances? Well, every once here, I'll show you guys how I thought about this, which is they did not tell you exactly what the angle is. Did you guys notice that? They didn't actually give you any numbers. No. So this could have been a really steep incline, or maybe it was a really shallow incline where you barely even notice it. Right? Could have been either one of those, and they didn't even say which one it was. Right? It gets a little flat over here. Right? So, guys, what if you had a block and you had a fan here? Oh, fan, right? And the fan had a really weak force. So the force on the fan was really weak, right? And this just zooms down, and then because the force is so weak, it slows down the fan very slowly, and it just keeps going and going for like a mile before it eventually comes to a stop. Could that be true? In this case, d2 would be much greater than d1. d1, maybe d2 is like this. It's like d2. That could be true, right? Right. But what if you did this instead? Okay. What if your slope was very shallow, so that even if there was no fan, the block would not accumulate very much speed at all before it comes to the end. Switch the block here. But the fan, let's say furthermore, what if the force of the fan is actually really big? So the force from the fan is slowing down this block in a hurry. What if it's just like creeping towards the bottom just very slowly, right? And then hits the bottom and comes to a stop relatively quickly. So that d2 is just real short. That could also be true too, couldn't it? Okay. So do you guys see how there's like an ambiguous situation? It depends what the variables are. It depends what is this angle from the vertical. Okay. It depends how strong is the fan blowing. Now, maybe if you knew those things, you might be able to actually start to get a numerical answer and actually compare these two. But I think as it's given, this is ambiguous. And every once in a while, AP will do this. They'll give you something that is ambiguous. And I think they want to see, like, can you think critically? Can you realize that this is an unanswerable question? Right, so, yeah, could be any of those options. Yeah, looks like overall you guys did pretty good. Looks like the plurality got this one. All right, any question about the fan? Spaceship moving in a straight line with constant velocity v. I like spaceship questions because you're out in deep space. There's no gravitational forces. There's no frictional forces. Okay. The spaceship has an acceleration that's directed opposite of the velocity. Ooh. Okay, so is the spaceship speeding up or slowing down? It is slowing down. It's slowing down. You know what, just an extra question. I want to think, what would it feel like inside that spaceship? I suppose you have here, I'll draw it as a box. Right. And let's say the spaceship is moving to the right, so I'll give it a rightward velocity. Right. Because if it has a leftward acceleration, suppose it has jet engines on all sides, so it's got some there, got some here. Right. Right. So it can like blast its engines any direction it wants to. Guys, which way is it actually blasting its engines?
Towards the velocity.
Yeah, yeah. You saw some like fire and smoke. You see all like going that way. Right. Right. So that it would have a leftward acceleration, since it would be slowing down. That would be slowing down, right? Right. Also, uh, guys, which way would be the floor? Like if there's a bunch of astronauts inside, would they be standing on the floor? And which side would be the floor? The top, bottom, right, or left?
Right.
Yeah, the right side. So everybody's standing on the floor like this. Yeah, you guys see it? That would be the floor. Right. Right, so that's what's going on. Now where are they going here? Which of the following statements about the change in kinetic energy is correct? Right. So, well, I know that here, let's see if we can figure out before we even look at the answers here. I know that kinetic energy is 1/2 mv squared. Right, here we go. Right. So the fact that the speed is decreasing, you guys said that already. Right, the mass is staying the same. Ah, when the overall kinetic energy have to be decreasing? Right, I think so. I think so. Yeah. Actually, if you want to get really strict about it, I think if they're blowing some jet fuel out, what's not, some rocket fuel, maybe the mass is also going down a little bit too. But however you think of it, I think the kinetic energy should be decreasing. Yeah, must be decreasing. All right. Oh, yeah, almost everybody got that anyway. All right, nice. Uh, ooh, two identical blocks, like distance d across a rough horizontal surface. Okay, so there must be friction, as shown. Block A, initial velocity do not. Block B had half of that initial velocity. Both blocks are still moving after sliding a distance d. Guys, if they're still moving, then at the end of that distance move, they still have some kinetic energy going on, right? Right. And there's probably a frictional loss, I think, but it looks like the friction didn't take all the energy out of the system. Which of the following is a correct expression for the power generated by the friction between block A and the surface and by block B and the surface? Power. Um, here. Well, what do the answer choices say? So I can get. Okay. So it looks like we're comparing the powers. Because I thought, well, how could you actually solve this if you don't have any numbers? But they just set up some inequalities. You guys see that? So something about an inequality. So we can compare it. All right. Well, what do I know about power? I know kind of two perspectives on power. I know that power is work per time. I also know you can rearrange power to get like force times velocity. Right? Now, if those blocks are the same, um, here, think about this from the side. Okay. So let's just create a generic block as let's move it to the right. So something about rightward velocity. Okay. Let's get a diagram going on this block. I bet this block can have its own weight, mg. I bet there could be a normal force here, Fn. And I bet there's a friction force, F sub Fr, that's like slowing it down. Isn't that true? Right? So if I took that friction force, maybe that's the same for both blocks, and I said times maybe the average velocity, that could tell me something about power. Right? Or another way to do this is I could say this friction force times the total distance moved. If this is like d, right, that could be the work done. And I bet it'd be the same work, right? Because I bet they have the same friction force for the same distance. You guys think that's the exact same work that's done by friction? It would be negative work, it'd be taking energy out. But it'd be in different times. So whichever one takes more time would be less power. Isn't that also true? Is it? Right. So there's two ways that here, I'll say both ways again, different ways to think about this. So one way to think about it is force times velocity. Now, if they have the same friction force, then whichever one has the smaller average velocity would be the smaller power, right? Right. The other way to think of it is work over time. And work is force times distance. So it's the same friction force for the same distance, so it's the same work. But whichever one takes more time to bring it to a stop would be less overall power bringing it to a stop, right? And when I say less, I'm saying closer to zero because these are all negative values. But the work, the power are all negative because it's taking energy out. It's doing negative work on the block. Okay. So, do you guys see block B is moving slower? So, guys, does it take block B more time to reach the end of that distance interval? Yeah, it takes it more time. Also, its average speed would be smaller anyway, right? So I think the power on B would be less than the power on A. Do you guys think that would be true? Right. Now, the exact values, well, I'd have to tag some numbers to it to be able to solve it exactly. But I think power B is less than power A. Yeah. Okay. You guys good?
Peter, thank you very much.
All right. Number 9. Astronaut on a space station throws a ball diameter 0.3 meters toward a wall. The ball travels in a straight line, distance of 1 meter before colliding with the wall. Immediately before hitting the wall, there's kinetic energy 1.5 joules. The ball exerts a force of 5 newtons, after which the ball rebounds with kinetic energy 1 joule. How much did the internal energy of the ball wall system increase during the collision? Ball wall system. Huh. Okay. Here, internal energy. Right, so I think probably how I would have phrased this question is how much energy was transferred to thermal energy, maybe something like that. Right? Because guys, if you measure the temperature of the wall, do you think the temperature goes up a little bit? Something like that, right? And there's a way to calculate that also through physics. It's like MC delta Q. Right? But if you look at the difference here in kinetic energy, that's say mechanical energy, that would tell you how much energy was transferred. You guys see there was a transfer of like a half a joule, right? And that's all they're looking for. A half a joule was transferred. Okay. All right, you guys go there? All right. All right. Quite a few guys looks like picked option C. And I think what would have led to that is if you were thinking in terms of vectors. But guys, is energy a scalar or a vector?
Yeah.
Energy is a scalar. So, like kinetic energy, it doesn't matter which direction it's moving. You only consider the positive values. So in this case, you just take a straight difference. Like if they gave you velocities or something, that kind of mindset would lead you towards like an answer C. But yeah, these are energies. So kinetic energy, just take the difference. All right. Ooh. Figure 1, block mass M, speed V, reach the bottom of a ramp. When the block reaches the top of the ramp, the height of the block is increased by h, the gravitational potential energy of the block Earth system has changed by amount delta U. In figure 2, we've got twice the mass, but half the speed. When the block reaches the top of the ramp, the height increases by so much, and we got gravitational potential energy increased by delta U G2. Right, so we got delta U1 and delta U2. Which of the following correctly relates those changes in potential energies? Okay. Yeah, could have asked maybe even harder questions. Here, let's work our way around this. Can I ask you guys some different things about this? Guys, could you say first, what if, here, I want to ask this. Okay. Guys, do you know for sure, let's start with figure 2. Do you know for sure if this block at the top is at rest or not? Is maximum height? Yeah, you don't actually know. It might still, it might be, right? Or it might still be in motion and it's gonna like fly off the end. It could do that, right? Right? They didn't indicate either way, right? All right. Now for figure 1, guys, for figure 1, do you know for sure that it's still in motion? Well, tell you what, if there's no friction, then you would, because here's how. Do you guys see how block 1 is going faster than block 2? Right? If there's no frictional loss, then that means that um, it would also have to be moving faster than the other block at the top, right? And if figure two, if it did just reach the very top of its motion here, if it maxed out its height, then block one would still be in motion. Right? You could show it with a conservation of energy setup also. Right. Um, okay, here. All they asked was about potential energy though. So, guys, what's the formula for again for potential energy? MGH, right? And they have the same height and they're in the same gravity field, but they have different masses. So for figure two, guys, figure two would have exactly how much more potential energy? Yeah, twice as much. So if it's MGH on figure one, it's 2 MGH on figure two. So it's the ratio 2 to 1. It's twice the mass and all else equal. Okay? Because we're just focused on potential energy, nothing else. So let's see if there's something that says like that. Yeah, that's exactly what it says. Okay? Twice the potential energy. Okay. Number 7, 2 blocks, M and 2M, initially at rest on a horizontal surface. Oh, there's no friction. The block mass M, slides distance D by a constant horizontal force F. Block 2M is pull distance D by the same force. What's the ratio of the work done? Guys, what's the definition of work? Work is what times what? Force times distance, right? Guys, did they say it's the same force? It says the same force. Did they say it's the same distance? Same distance. Guys, if it's the same force but the same distance, then how does the work compare? It's the same. It's got to be the same. Right? Yeah, so 1 to 1. Right? Now, what I think would be an interesting question is what's the ratio of the speeds? What do you guys think the ratio of the speeds would be? I think it's similar to what we did earlier. Had like a square root in it. Okay. Actually, guys, I think it could be answered pretty much by this. Because then they say the only difference is one block has twice the mass of the other block. Right? So it's the same work and just double the mass. I think the ratio of speeds should be like square root of 2. Right? The less mass the block would be moving faster. So that could also be answered by that. Right, number 6. Car A, B, and C, same mass. Car A is moving with speed v in the negative x direction. Car B is at rest. Car C in the positive x direction. We're just following correctly ranks kinetic energy of the 3 carts. Oh, okay. Guys, does the direction ever matter for kinetic energy? No, because kinetic energy is a scalar value, right? The fact that car B is at rest, what is its kinetic energy equal to always? 0, because 1/2 mv squared. If the v is 0, energy is 0, kinetic energy is 0. So kinetic energy is 0 in car B. The cars A and C would have the same energy. They're just moving opposite directions, but same speed, same mass, same speed. At time 1, cart mass M being pushed has straight level track, has speed v. A short time later, it's 3v. Which of the following expressions is equal to the average power delivered during that time interval? Okay. They said some time later? Yeah. Okay. So here, I think I can figure this out. Okay, and it should be something right here, right? Wait a minute. Oh, no, you know what? Okay, it starts with this, but it's a little trickier. Guys, work could be a change in kinetic energy, right? So I'm going to go through work energy theorem. That's what I'm going to do. I'm going to say the work done is equal to the change in kinetic energy. Okay, right. And then the power is work over time. So it's 1/2 mv2 squared minus 1/2 mv1 squared. And the time interval would be T2 minus T1. Okay. That might be the answer I'm looking for. Do you guys see where I got all that from? I have changing kinetic energy in the numerator and the time interval in the denominator, and that tells me the power. All right. I think that's they want. Okay, they did a little more work with that. Oh, B to 3V. That's what we got. B to 3V. Here, I'll finish solving this out then. Okay, so this V here is 3v1. Now that's being squared, right? So I'll pull 1/2 n out. 1/2 n. Hey guys, what's 3 squared? 9. All over t2 minus t1. Right. And what guys, what's 9 minus 1? 8. What's half of 8? 4. And that's b squared t2 minus t1. Right, so no, hey, take 2. Let me see if I think that's what they said it was. Yeah, that's it. All right. You guys have a good day. And tomorrow will be please lab.